you can pinpoint the evolution of plants and plant life on planet Earth as a moment in time where the climate changed.
Yeah, so that's meant to be, that's one of the main mechanisms that, because Earth didn't have this before, was this new carbon sink, this new way to draw carbon down from the atmosphere. And so when it happened over sort of the evolution of plants over maybe, say, 10 to 80 million years, it is thought to have cooled the Earth by sort of 5 or 6 degrees.
Hi and welcome to Wonder, the Planet Earth podcast for the curious. I'm Holly Cooke, joined as always by fellow Earth scientist Dr Anthony Reid. Now, Anthony, opposite us today is Dr Andrew Merdith, research fellow at the University of Adelaide. Now, I am really looking forward to this conversation, and I'm actually going to take you back to 6 o'clock this morning to kind of frame why. Are you ready for this? This is actually a bit rogue, but I think that this will tie in well. I woke up this morning early and I needed a bit of calm and stability in my life. It's been a bit hectic. And what I did is I took a nice hot shower and I looked out the window that is right next to the shower, and I saw this kookaburra against the dark blue silhouette. It was actually like this black silhouette against the dark blue of the morning sky. And I just had this thought of I felt really grounded is what I felt. I felt grounded and I felt calm, and I felt like as a geologist I was connecting to a sense of stability out there, you know, a sense that things have always been like this, and I just needed to come back into tune with how things in nature are, which is constant. Andrew, your work would think to the contrary, actually, in a really magnificent way, because Andrew, what you do is you think about the Earth in deep time, not on hundreds of years, not on thousands of years, but you think about how the Earth has changed over millions and billions of years. So can you talk to that? Why is my sense of stability in nature so misguided in this sense?
Well, I don't know if it's actually misguided. It's sort of a sense of timeframes. We live short lives on Earth, and over short timescales, Earth is reasonably stable. We don't actually see that much change in terms of a global scale tectonic geology sense over these timescales. We only see that sort of scale of change that we look at in research over much longer timescales, over millions or tens or hundreds of millions of years. So I think that's quite natural. I mean, I'd go on bushwalks, I'd go to the beach, I'd take my little toddler down to the park and he runs around chasing birds, and it is very grounded. Like the grass grows to the same length, the trees are there, the birds are there.
And thus it always has been in some sense.
Yeah, well, at least for my life.
Yeah.
At least for your life, but not for your research. So this is fast. So I'm glad that someone else is like seeking out to nature to feel some sense of calm. So then why then does the Earth change like this? So on our timescales, it's nice and slow and it's nice and, you know, constant. Then Andrew, what do you know about it not being constant?
Well, so I guess on the biggest picture you could imagine, like if you zoom all the way out of Earth to space and then you look at Earth as a planet, I think it comes down to sort of a very basic idea. Earth is really, really hot. It has the cause thousands of degrees in temperature, and space is really, really cold, and hot things want to lose that temperature to reach an equilibrium. And so a lot of the big changes that we see over Earth history over the last 4.5 billion years are probably, well, in some ways, many ways, fundamentally driven by the fact that Earth is hot and it wants to get cold. It's like putting out a I don't know, a pie on the windowsill on a cold winter's day. It eventually loses all that heat, and that sort of drives what we see happening underneath us in the Earth. So part of the Earth layer called the mantle, it convects, and that's just a way for it to lose heat. And at the surface, we see that expressed in plate tectonics, in things like subduction zones and mid-ocean ridges. And what we see, what effect of those we see on the surface, things like mountain ranges and plates moving around.
Wow, what a wonderful thing. Isn't that really weird to think about, how all of the complexity and richness and vibrancy and the mountains building and the oceans forming and then oceans destroying, all of that can come down to a relatively simple principle, which is...
We're talking about pies already.
Correct. It's nearly dinner time.
Yeah, I know, it's nearly
so hungry on this podcast.
The Earth is just a pie trying to lose its heat, but it does that in a really magnificent, complicated way. Fantastic. So, like, you're in this line of work. What a cool line of work. What's your backstory here?
It's funny, I guess, the path you take to get to different places. So I actually originally studied to become a high school teacher.
Uh-huh.
I did a little bit of earth science in high school in Sydney in year 11 and 12, and I really enjoyed it. I remember sitting in chemistry actually thinking about what I was going to do at university, And I said, I probably won't be a high school teacher, so I won't worry about that.
Why?
I don't know.
You got uninspired by being actually in high school.
And yeah, maybe I won't mention what school I went to.
It is a bit sad, but anyway, that's another.
Yeah. So as I thought about it more, I decided actually, maybe I will be a high school teacher because it wasn't my first choice. I think I wanted to be a medical doctor, but I wasn't smart enough.
And now we're all here around the table.
Oh, yeah, it's not a great sell. Sorry. And eventually, actually, I would say that there were a few teachers I had at high school that I don't know if inspired the right view, but I enjoyed being in their class and I really liked them and I thought I got on well with them. And I was like, maybe that would be interesting to do. And so I put down high school teaching and I went to university to be a high school teacher, going to teach geology or earth science and chemistry. But
then you got too distracted by the actual subject matter. Instead of teaching it, you decided to research it? Or
pretty much. It's just, for me, I guess a lot of my research is driven by really small questions. It's kind of like waking up and walking out your house and seeing something and being like, I wonder why it's like that. And like, not just kind of like, there's a rock there or a bird there, but like, why actually is there a kookaburra in the first place? Like why does Australia have all these different birds and parrots? And I lived in England for a few years and like, they didn't have that many parrots or birds there besides pigeons, and so
nothing wrong with the pigeons. They got their own.
Well, nothing wrong with pigeons, especially little crested ones.
They're pretty cute. They're pretty cute.
So parrots are great.
So I was sitting in a third year sedimentology class, and the lecturer, who still works at Sydney University, Dr Andrew Merdith, walked in, and I was usually late to my lectures because I probably, again, wasn't the best student. Maybe not the best thing to sell, but I was getting better. This is as I was getting better, I was going through.
Sharpened up.
Grading you.
Sharpened up. And I turned up on time and she said, by the way, before I start the lecture, I'm offering an honours project next year. It's on Australian sedimentary opal. And then she said, we don't really know anything about it except that people mine it and sell it. So we're kind of going to try and figure out something about it. And I was like, that actually sounds kind of interesting. I wonder why there is opal in Central Australia. And then I thought about it, but like I'd already done my teaching practice and I was really enjoying it. And I was like, I better just email and just be like, can I come for a chat? Then I came for a chat, and then the next thing I knew, I said that I'd do honours. Did honours, and then
awesome. What'd you find out about opal? I'm literally here with my opal ring that my family gave me for a birthday. What'd you find?
That it's
no. Just break my heart. Do it.
You have to be very careful with it with jewelry because it can. If you put it in soap or water or leave it in the sun, it can wreck because it's hydrous.
I do so many dishes. I do so many dishes.
You should take it off.
You do the dishes.
Take it off.
Okay, so that's the honours done.
Or wear opal earrings.
Yeah, correct. Well, take it off in the shower.
Take it off in the shower. Or the beach, or the salt water.
I can't do that. I can barely remember to feed myself, let alone take off jewelry. Right, so opals, but then
okay, that's a very big difference between like opals and paleoclimate and paleotectonics. How did you connect those two?
Yeah, so part of my project with opal was to look at, I guess it's sort of data analysis around. I did a bit of field work and a bit of geochemistry and petrology, and then there was a component sort of on at the time was like data mining, I think was the in word in 2011. And I was sort of looking at the paleo environment of opal and how it changed through time and whether that could have something to do with why it's only found in Australia and essentially nowhere else in the world.
Interesting. Did you go to Cooke?
I went to Lightning Ridge, Winton and Opalton.
Craft.
They were
famous.
They were great. Yeah.
These famous great metropolises in the Central
Hotel in Winton. Amazing.
Absolute classic.
And just to zoom in on that point, only found in Australia. So to your point about little questions guiding your research, right there, my brain goes, that is strange. Well, that's not just a random thing. Why is it only found in Australia? Is that one of those questions that got you thinking, like, what is controlling these things?
Yeah, that was sort of like, that was the question that I guess Adriana posed in the lecture is like, we don't know much about it and we're wondering why it forms. And that was a little question where I was like, I actually have no idea at all. And then it sparked my curiosity and my project sort of went, I guess, in that general area. And then I stopped doing science. I went back to finish my teaching degree. And then I was like, well, maybe I won't be a scientist. I'll go back and do teaching. But then I found like just even in my last year of university finishing off, there was still lots of little small questions that came up. Now I was going back to finish off some third year subjects. And then I took a bit of time to think about it. And then my eventual PhD supervisor advertised a project and emailed me and said, if you're interested, I think you'd be good at this. Because it was sort of looking at, I guess, big data in the Neoproterozoic and data synthesis and building models and understanding how different things had happened. And yeah, I thought about it and said, yeah, okay, that sounds pretty interesting.
Let's do it.
Let's go.
And go the adventure.
And that was in probably late 2013, and then I started in 2014, and
off you went.
Fantastic.
Off I went.
Fantastic. Is there a big difference between so you mentioned the word Neoproterozoic there?
Yes.
So that means something which is older than...
So the Neoproterozoic, it's a period of Earth of time in Earth's history. So if you imagine Earth has a lifespan from when it first formed about 4.5 billion years ago to present day, the current sort of eon we're in is the Phanerozoic, and that went from 540 million years ago to present day. The Neoproterozoic was the one before that. So that was from a billion years ago to 540 million years ago.
Huge.
So
1 billion to 540.
Yeah.
And that contrasts with 540 to now.
Yeah.
What's why? And what's the difference between the two? And also, when was the opal formed?
Whoa. That's a question
good question.
sandwich.
So maybe what's the easiest way to answer this? So the opal formed, I think it still hasn't been dated properly, but there's been different ideas pushed around. Some people like it forming really old and it sort of sits there and comes up to the surface and then is found. Other people say it forms quite young. You get fresh rock that's unweathered, so it's still essentially its primary components. It hasn't been exposed to water or sort of oxygen too much. And as it comes to the surface, it's a weathering process that forms opal. So essentially, as rock is exposed at the surface, opal forms, and then as it erodes, so as it breaks down and is sort of carried away by rivers, then the opal disappears and you expose new rock that then gets weathered and more opal forms.
Interesting. But that's not happening in the Neoproterozoic.
No, that's not happening. Well, it might have been. I'm not sure. I guess.
We haven't preserved from the Neoproterozoic.
It's not preserved in the Neoproterozoic. So the main difference, the main transition from the Neoproterozoic to the Phanerozoic is that we see essentially modern complex animal life.
Animals.
Forming. So right at the end of the Neoproterozoic, there's a time period called the Ediacaran, and that's where animals first formed, but they were, they were quite simple. And then in the Cambrian we have, which is the time period directly after the Neoproterozoic, from about 540 to 480 MA, we have what's called the Cambrian explosion, where it's sort of like life kind of just turned on and
exploded.
And so we see almost all modern groups of animals. So like things like the early forms of mammals and reptiles, or probably tetrapods or chordata, animals that have spinal columns. We see corals and sponges and things that eventually became insects. They all sort of formed in the Cambrian.
Crazy, isn't it?
Wow. Yep. So a real need to break up those two chapters in Earth history right there. Yep. The explosion of animal life.
Okay. Now I've got a couple other things. So what we really want to talk about with you is the relationship between these long-term trends in the way the Earth has moved and the dance, if you like, of the various tectonic plates, and how that has affected two things. One is the climate, how the climate system has changed, and also how that has affected life. Now, we may not get all the way into the details of life, but let's just try and understand at first climate, because that's a really, really important thing to understand.
Like geological climate, time scale of these millions, billions of years of the whole planet. What's geological climate?
Because I was in the taxi the other day on my way to the airport to Perth, and the taxi driver said to me, so he asked what I did. I said I was a geologist. I've had this conversation a thousand times. What do you do? I'm a geologist. I always wonder whether, is he going to be into creationism and think that Earth's a few thousand years old, or is he or she going to be interested? And this bloke was particularly interested, and we had a great conversation about it. And he really was like, climate, but climate has changed in the past, and what does it mean? He was really trying to understand, because often people don't get access to these deeper kind of the deep time perspective, but they confuse that deep time perspective with what's going on right now. So that's two things, but let's delve into the deep time perspective with you. So,
not the kookaburra at 6 o'clock this morning.
Okay.
Go back.
Okay, so I guess the story with climate probably starts with carbon.
Okay, so yes.
Carbon's an element.
I feel like we're in year 12.
I'm ready for it.
We're back in year 12.
So
carbon cycle.
Carbon's it's an element on the periodic table, and it's the basic building block of life, but it's also sort of the main control over Earth's climate over long times. And the problem starts, well, I guess it's the problem, and it was this sort of paradox that was around for a long time about the faint young sun.
Ooh.
Faint young sun.
The faint young sun.
Like the sun.
The sun.
That sounds like an album title.
So-
Isn't that a Creedence Clearwater?
It probably is the faint young sun. Oh, I mean, you should make a song out of it.
So the idea is that when stars form and they're younger, they're less hot. Essentially, they burn a little bit less intensely, and as they age, they get brighter and brighter and brighter, and which is fine. But we know from looking at the rock record that we think from looking at the rock record that liquid water has been on Earth more or less continuously for 4 billion years. And if you look at how hot the sun was back in time at 4 billion years ago, and you look at the distance the Earth is from the sun, Earth should be really cold. Like there shouldn't be any liquid water. It should be frozen at Earth's surface. And so this led to this kind of paradox. How can you have a much cooler sun, but still have an Earth warm enough to have liquid water? And the answer to that essentially comes from carbon, from greenhouse gases, in particular CO2, which over long time scales is the main greenhouse gas. And that essentially is how we get around that paradox. We know there was probably a lot of carbon dioxide or a lot of other greenhouse gases in the atmosphere at the time, enough that it formed enough of a thermal blanket to essentially keep Earth's surface temperature within that range of liquid water, so from 0 to 100 degrees Celsius, which is sort of known as the habitable zone for life. And that's also like, that's one of the key things that people look for on exoplanets, for example. Like, because if you have enough of these specific gases in the atmosphere, then your planet might be at the right temperature where you can support liquid water. And if you have liquid water, that's sort of the basic building, it's not the basic building block of life, but it's sort of the basic home of life, essentially, primitive life like that we see.
Right. What an eloquent thing to say that the story of climate can begin with an understanding of carbon. So I imagine then tracking the activity of carbon over this wonderful lifespan of the Earth becomes a fairly central question to tracking what the Earth's climate has done. So do you engage in that kind of tracking of what carbon is doing?
Yeah. So we can look. So again, we have carbon, and then we have what we see in the rocks, and we can see in the rock record that Earth's climate does change a lot. And the easiest way.
What's an example where you can see, oh, this is cold,
and this is hot?
You can look at a rock and say, oh, that was cold, and then another rock you say, oh, that must have been hot.
Yeah. So the main information we have is it will be from glacial deposits.
I see.
If you're lucky enough to live in Adelaide, you don't have to look very hard or go very far. You can just walk to the beaches or up to the Flinders, and you see these beautiful examples of rocks that we're pretty sure formed in a world where it was cold enough to have glaciers grinding over the rocks, leaving big scratches or big grooves, or then eventually melting when they got low enough and dropping out big random stones in the middle of nowhere. And that's the best sort of evidence we have for past climate change, because to have sort of these big glaciers, it needs to be really, really cold. You need to have sort of a mean annual temperature of sort of -10, -8 degrees. If it's any warmer than that, the glaciers can't accumulate enough mass over the summers, essentially, or they don't get deep enough off the mountains to come down and leave these bits of evidence. And so anything, if you see glacial evidence of glacial, it's cold. It's below freezing on average over the year.
Wow, huge. So when it's really, really cold, you see these rocks, like you see glacial deposits, and when it's hot, what do you see in a hot world?
That is a good question. You don't see anything quite as direct as that, but you might see. So I guess if there's no glaciers and there's no ice stored on continents, then you have usually much higher sea levels. So you might see. I guess a technical term would be a marine transgression.
So sea level rise.
Sea level rise, yeah. So if you take all the ice and you melt it, goes into the ocean, sea level then goes up, and you start getting essentially, if you go to the beach and you see there's all the sand, and if you walk out far enough, eventually it might get finer and turn more to mud or silt or clay. And so we can see when the sea level is higher, we essentially see that the beach goes inland a little bit, and then you see this sort of progression of rocks that change based on how far inland you go.
Right. And so those oscillations between a super hot world and a super cold world are in no small part controlled by carbon dioxide in the atmosphere. They
are controlled by carbon dioxide.
They are controlled by, right. So they are controlled by carbon dioxide. So how does it get into the atmosphere, or like on geological timescales?
Yeah.
How does it get in and how does it come out? Because we see evidence for both in time. So how's it gone between those two states?
Yeah. So the way that I think about it is that you have a source of carbon. So you have places that carbon go into the atmosphere, And then you have places that sink carbon, so places that take carbon from the atmosphere and put it into essentially the earth.
Rocks.
Yeah. The main sources of carbon over geological time are essentially where we see rocks breaking or we see rocks melting. And that happens mostly at places like mid-ocean ridges, where you have melted rock that cools and becomes ocean crust.
So volcanoes?
We see it, volcanoes. So, you have standalone volcanoes, for example, like in Australia, maybe at Mount Gambier or somewhere. They'll sort of have some sort of melted rock in there that will have some carbon content and that'll release. And then really spectacularly along things like the Pacific Ring of Fire. So going from the southern Andes all the way up through America, across to East Asia, and then sort of down all the way into Papua New Guinea, and then coming down all the way through New Zealand. These are meant to be really big reservoirs of carbon that get melted and then put into the atmosphere.
Weird. So volcanoes are like this link between what we call like deep carbon and carbon in the atmosphere that goes towards warming the planet. Wait. So that's warming the planet and cooling a planet then. How do you bring it back down into the earth? So we mentioned it goes into rocks. Does that mean you break apart the rock? Like how do you actually what do you mean you get carbon into rocks?
Yeah, so that's the source of carbon, would say, is sort of through that process or processes like that. And then we have sinks of carbon, and there are two main sinks of carbon that we look at over geological timescales. So over sort of 1 to 10 to hundreds of millions of years. The first one is the organic carbon cycle, which, as the name suggests, it's through organic processes, and the main one is photosynthesis with plants. And so plants photosynthesize, they take CO2 from the atmosphere and water from the ground, and in sunlight they produce oxygen and energy. And that CO2 is stored in plants essentially as plant matter. That's pretty much like
cell walls, leaves,
bark, trunks.
And
so when plants die,
bones,
our bones, animals,
fleshy bits,
pretty much like most of life is carbon. That's all comes eventually from.
You're nothing but a sink. That's all you are.
Big carbon sink.
One big tiny sink.
Awesome. So wow. So it's actually stored up. So there's this organic carbon cycle where we bring carbon. Well, carbon is brought from the atmosphere and kind of locked up
in
organic matter in life.
In life. Yeah.
And then eventually the life dies and it gets buried, and that forms different types of rocks that we see on Earth's surface. And that's one trap of carbon. That's one sink of carbon.
Such as coal or
swamps,
coal, oil,
heat,
gas,
heat,
all that
swamps,
sort of stuff.
Yep. This is all the organic carbon cycle,
all
trapping
the
carbon in Earth's surface. And if you look at sort of when plants evolved, you can actually, what we think happens is that the temperature dropped quite a bit because
that is very interesting.
There wasn't that much photosynthesis. Well, there was a lot of photosynthesis, but it wasn't trapping as much organic matter until plants evolved. And then it's thought to be one of the main cooling mechanisms that happened about 400 million years ago.
You're right, Anthony. That is absolutely fascinating. So we're saying if I can just link this back, I sometimes get lost in my own questions. So if we want to think about how the Earth's big geological climate states have swung greenhouse, which is a really warm world, to an ice house, which is like, in worst case, snowball flying through space kind of thing, you can pinpoint the evolution of plants and plant life on planet Earth as a moment in time where the climate changed.
Yeah. So that's meant to be, that's one of the main mechanisms that, because Earth didn't have this before, was this new carbon sink, this new way to draw carbon down from the atmosphere. And so when it happened over sort of the evolution of plants over maybe say 10 to 80 million years, it is thought to have cooled the Earth by sort of 5 or 6 degrees.
Yeah, really cool.
Now there's another there's another sink of carbon that you haven't mentioned for us.
So in the very original way of naming things, the other sink is called the inorganic carbon cycle.
Keep it simple. I don't mind that.
Okay.
I can probably remember that for the exam later.
It is a very good way to. So organic through organic processes.
We have to remember this for the exam because
inorganic.
He's going to give us the test afterwards.
There'll be a questionnaire later. So the inorganic carbon cycle is it's essentially functionally it's the same thing. It's a way of taking carbon from the atmosphere and trapping it in rocks, but instead of using organic processes like photosynthesis, it uses inorganic processes. And this is sort of the process that's been on essentially for as long as Earth's been, and it's thought to be as long as Earth is here, it'll be the main sort of sink of carbon.
What is this process?
Yes, please.
Yeah.
This is an awesome build-up.
Yeah, build it up.
I hope it's got to live up to its
Literally build it up.
expectations. So the inorganic carbon cycle. So again, it comes actually back. It's fascinating. It comes back to rocks. So you have rocks are fundamentally just made of elements. Different elements make up different minerals make up different rocks. And there's two elements in particular, calcium and magnesium, that are found in some rocks. And they're really, really important. These rocks are often on land. When they're on land, they erode and they weather. And that just means that you have a rock and you sort of break it down. So if you live, probably not in Adelaide, but somewhere else where there's really soft rock, like made up of sand, you can sort of crunch it in your hands and break it into little grains.
Mm-hmm.
That's sort of like a physical erosion. You're breaking the rock up into these little bits and pieces. And then weathering is when that sort of chemically erodes. So you sort of break down those grains into its chemical constituents.
I'm picturing something like a very wet environment, like if I lived in the Amazon,
Yes.
or in Bangkok in the monsoon or somewhere like that,
Yeah.
and I'd go outside and I'd put a spade into it and come up with this thick,
Just disaggregated rock.
gloopy layer of clays. That's weathering, right?
Yeah. So areas that are very wet and areas that are very hot and humid thing that breaks down rocks really quickly. And so there's very high weathering rates, usually around the equator.
Yep.
That's where it's really wet and humid.
Mm-hmm.
And then as you get drier and you get colder, they both sort of drop off quite a bit and there's not much weathering or erosion.
So how does weathering relate to magnesium and calcium?
Yeah. So there are some, not all rocks are like this, but some rocks on Earth's surface will have lots of magnesium and calcium. And so when they break down, those magnesium and calcium elements are transported in rivers, in streams. They eventually, over time, make their way into the oceans. And there they form another sort of rock called limestone. That's essentially the main drawdown of CO2. So carbon dioxide's in the atmosphere. It equilibrates with carbon dioxide dissolved in the oceans. And in the oceans, when it's there, it reacts with free magnesium and calcium ions to form magnesium or calcium carbonate.
Carbonate rock. It just forms rocks. It's literally getting locked in the rocks in the ocean.
Just gets locked into rocks in the ocean. And this has happened as well, what we assume has happened for most of Earth history. As long as you have magnesium and calcium rocks on the surface and you have some sort of weathering process that takes them into the ocean and you have CO2 that in the ocean and the atmosphere, this will sort of draw down that carbon dioxide
Right.
over time.
So do you then care much when you think about, because what I'd eventually like to get to is that you do think about how the Earth looked, and by looked, like where was the land? Was it all aggregated and clustered together, or was it dispersed around? Was it high? Were there mountains? Was it low? Were there basins? Do you then care about what land is doing when you think about when the Earth can get really cold, has gotten really cold in time?
Yeah. So that's the simple part of the story, which is that's a simple part of the story, and it gets complex in the details because the rate, which is how much erosion or weathering might happen, will change depending where you are on Earth. So as we said, if you're in the Amazon or northeast Queensland or Papua New Guinea, or even most of the eastern side of Australia, we get lots of rain and it's a bit more humid, your weathering and erosion rate will be much, much higher. And if you happen to be in the desert where there's no rain, then it's going to be very, very low. And if you're in somewhere like Antarctica, then it's going to be functionally zero. Maybe not quite zero, but it'll be there's just no erosion or no weathering because there's no real breakdown of rock and transport to the oceans. So depending where you have your continents and where you have your mountains and what your weather and what your climate patterns are will change how much weathering and erosion you actually get.
How interesting. So what we're getting to here is the idea that the actual tectonic architecture, the shape and geometry and the kind of even the places, the latitude and longitude of different continents over time has a massive effect on both the organic and inorganic. Should I get that?
Yeah.
The organic and inorganic carbon cycle, which affects climate.
Yeah. So the biggest sort of climate change event we've seen in Earth history is this thing called Snowball Earth, which is what Holly mentioned earlier about the snowball flying through space. And that's essentially where based on the rocks that we see, we think that Earth was essentially completely covered in snow and glaciers. There were glaciers extending all the way to the equator. There might have been little pockets that weren't fully glaciated, but functionally the entire Earth was covered in snow. And there are a few ideas about why this happened. And one of them is that you had all the continents on Earth were around the equator. So you had poles that were mostly continent-free. And then they started to break apart. They started to rift. So they started to break apart. It was at that time. And that caused a lot of new ocean basins to form, but it also caused a lot of it caused a lot of erosion and weathering of these new interiors. So if you imagine you have Australia and you have this big island continent, I guess, and you break it in half, all of Central Australia now has access to an ocean. It now has access to precipitation. And in order to transport the rocks in the center into that ocean to draw down carbon, they might only have to go 100 kilometers instead of a few thousand kilometers.
Oh my gosh. I just thought of what you said a couple of minutes ago, which was, this is the simple part of the story. And just as you say, like you do the analogy of, you have a big clump of land and you start to break it up, and a big clump of land, i.e. supercontinent kind of stuff. So you have a supercontinent and you start to break it up. You're just saying that you give it access to an ocean, you give it access to precipitation, you give it access to weathering, you add so many variables that begin to, there's a tectonic pulse at the center of it, but overlying that is a whole bunch of new landscape variables that go towards climate. That's nuts. How do you model this?
We try to model it. So I get
this is a lovely feature about good scientists, is that they're incredibly humble.
Oh yeah,
and they're
like Andrew, you're a legend.
To accept that it's possible. There are a lot of qualifying statements like that.
Leaving room for a very valid question,
which is difficult when you take that into the political sphere where people want absolute answers. Anyway, that's another conversation. But
it's too close to the election.
In the time left, let's just think about a little bit about that. Not the political thing, but other things.
Back to the climate. Back to those variables that you introduce and how you model these, how you try to model these.
Yeah. So I guess the project I'm working on now, and it's not just me, it's like people at Adelaide and there's people also in Australia and overseas as well that I'm working with. What we're trying to do essentially is to build a model that can sort of describe the Earth and how it's changed through time that we can then ask questions about. And so when we look at things like the inorganic and organic carbon cycle and degassing, they form this I guess the carbon cycle. And what we want to do, the end goal, is to be able to trace the carbon cycle over Earth history to see if we can predict how much carbon is coming out and going in and how that balances over time. And to do that, we're trying to do it very much from the ground up. So we're trying to build different models of Earth independently. So for example, one of them will be a paleogeographic or a plate tectonic reconstruction where we have the continents moving around on Earth's surface. And we have some idea about where the mountain ranges were and where the ocean basins were and how deep they were. And so that sort of gives us sort of the baseline, what Earth looked like back in time. So if you imagine, you can look at a map of Earth today and you can sort of see it's green and brown in some places and there's mountain ranges in places and the oceans are deep in some places and shallow in other places. We're trying to do that, but then using the data that we have in the rock record, what it might have looked like back in time.
That's insane. So you're trying to basically recreate how the Earth looked, not yesterday, not at 6 o'clock this morning with my kookaburra friend. You're looking at it through the deepest time I can stretch my mind to think about, which is on the million to billion year scale. Yeah.
So we're looking to do that over the last billion years.
Oh my God.
And then that sort of becomes our base model. And then with that, we can start to hopefully do other things. We can start to simulate climate. So again, on long time scales, if we look at climate is driven very strongly by things like where mountains were and how tall they were, where ocean basins were, how deep they were, and where the continents are around on Earth's surface. So whether you have a gateway, an oceanic gateway, which is where you have a very narrow passage, like the Drake's Passage, for example, where ocean currents can circulate, or you might have a land bridge like the Panama Isthmus, where there is no circulation between the Pacific and the Atlantic. That'll have very important implications for what the oceans and atmosphere are doing.
I would actually just say that's art. Like, I kind of think about it like a canvas. You have this canvas with which you bring in science and thinking and collaboration and a dash of humility to say, I don't know if I'm going to get this right, but we're going to give it a shot. Thinking about the Earth like that, I just think it's art.
Fantastic.
Thanks so much for coming in, Andrew. I've loved this chat, so thank you.
That's okay.